In this video, we're going to be introducing some more complex equilibrium calculations. So this video is just going to focus on the setup for those calculations, and then the next couple videos we'll talk about the different types of problems that we can solve, the different types of calculations we can do using the same setup. So we already have the tools of the equilibrium expression and the equilibrium constant under our belts. And what these things allow us to do is relate the initial state of the system to the equilibrium state of the system. So using our equilibrium expression and our equilibrium constant, together with a little bit of stoichiometry, if we know enough about the initial state of our system and just a little bit about the equilibrium state, we can figure out everything else about the system at equilibrium. So we use a setup method most commonly that's known as an ICE table for these types of calculations. So when you get a lot more proficient with these types of calculations, the ICE table is not strictly necessary, but it is the most streamlined way to set things up. So for right now, I do want to see your ICE tables when you're working on these types of problems. So ICE is an acronym, clearly, where I stands for initial. So these, or the I row, contains the starting concentrations of all reactants and products. The C stands for change. And this describes how the concentrations change between the initial and equilibrium state. So as your system approaches equilibrium. And when we're dealing with reversible reactions, we don't usually know how much the concentration is going to change. So we express this in terms of X. So X is our unknown concentration change that we don't know how much our concentration is going to change as we approach equilibrium, and that is part of what we're trying to figure out. And the last row, the E, is for equilibrium. Or sometimes you'll see it referred to as end, the end of the reaction. We can use the same type of setup for any stoichiometry problem, actually, where you may not really be establishing equilibrium. You might be completely consuming a limiting reactant. So that's not what we're doing right now, but it's another application for the same type of setup. So these are, or this row will contain the concentration of reactants and products, after your equilibrium has been reached. So once our system reaches equilibrium, if we know our concentration, they would go in the equilibrium row. Our concentrations at equilibrium, if we plug those into the equilibrium expression, we would be calculating the value of K. So essentially the way this works is that we know how much we started with. We have an expression for how much it changes. The initial row plus the change row is equal to the equilibrium row. So we know how much we started with. We have an expression for how much we gained or lost in the process, and the sum of those two things is what is left at equilibrium. So as an example, if we want to set up an ice table, we can use simple example, kind of generic example like this. We have a flask filled with 2 molar A and 2 molar B, which are allowed to react according to the equation below. So we've got A reacts with 2B in equilibrium with C and D. We can set up an ice table for this system. So ice tables typically have the reaction at the top. You will sometimes hear them referred to as rice tables, where the R is for reaction. I learned them as ice tables, so I still call them ice tables. Rice is a newer term. So we have our reaction at the top, and we set up the I, C, and E rows underneath. Personally, I don't usually include lines in my table just because I find it too much visual clutter. But you can include lines if you so choose, just to divide up your rows and columns. So we'll have a column for each reactant and product, because we'll need to list a concentration for each of these. And then we have our 3 rows, I, C, and E. So lines are optional, but to at least get us started, I'll draw them in there. So we are given initial concentrations in the problem here. So our flask is filled with 2 molar A and 2 molar B. So these are our initial concentrations. So that's how much we are putting in our system to start with. Don't do that in yellow, 2 molar A and 2 molar B. We're not told there's any C or D in the system, so we can assume that there is none. Note that C is a solid. Because C is a solid, it is not in our equilibrium expression. Which means it's not going to affect our equilibrium. So we can actually ignore it in our ice table as well. So this whole column, we can just not put anything in since it's not part of our equilibrium expression. We don't need to worry about that. So we can assume that there is no D present initially. So in our change row, we need to express how much our concentration is going to change in terms of X. So there are 2 things we need to know here. And the first is, which way is our reaction going to go? Which concentrations are going to increase and which concentrations are going to decrease as we approach equilibrium? So in this case, the 0 here is the key. We have no product present initially. So that means that our reaction has no choice but to go in the forward direction, meaning that we must produce product and producing product requires that you consume reactant. So as we approach equilibrium, the concentration of our product is going to increase, and the concentration of both of our reactants is going to decrease. Since we're producing product, that concentration goes up. Since we're consuming reactant, that concentration goes down. The next thing we need to think about is how much it's going to change by. We don't know. So we leave it in terms of X, but what we do know is the ratio between how much it's going to change for the different substances. And that depends on our coefficients. So for instance, we have invisible coefficients of 1 in front of A and D. So for every 1 mole of A that reacts, 2 moles of B react according to the coefficients. That's what the coefficients in a balanced reaction are telling us. So that means that for every 1 molecule of A that is consumed, 2 molecules of B get consumed. So the concentration of B is going to change twice as fast. So if we lose X amount of A, we are going to lose 2X amount of B. So whatever your coefficients are, just get carried down in front of the X. So the 1 we don't need to write in as usual, but the 2 we do, because this is getting used up twice as fast. Then for every 1A that is consumed, 1D is produced. So this concentration will increase by X. So the ICE table setup allows us to see all of these relationships at once, rather than doing out each calculation kind of as a separate line. So then if we started with 2 molar A and we consumed X, at equilibrium, we will have 2 minus X molar remaining. With B, if we started with 2 molar and we used up 2X, we will have 2 minus 2X molar remaining. And then for D, we started with nothing and we created X. So at equilibrium, we will have X molar present. So we're taking our coefficients down in front of our X's here to maintain that stoichiometric ratio. And this would be the type of setup that allows us to solve a couple different types of problems depending upon what additional information we have. This particular example, you don't have enough information to actually solve it at all, but more on that in the next couple of videos. So one more example that I would like you to try on your own first. So set up an ICE table for the reaction below using the initial concentrations that follow. So here are your initial concentrations, and here is your reaction. So take a minute or two and try to just set up an ICE table like the one we just did, filling in all of the boxes, filling in all of your rows with the appropriate expressions. So solving this one, we can set up our table once again. We will have initial, change, and equilibrium rows. And we'll need to create a column for each of our reactants and products. Again, lines optional. You can just write underneath is totally fine. And from here, we are given initial concentrations. We are told that the initial concentration for N2 is 0.1 molar. So that's going to go here. H2 is the same. O2 is 0.05. And we're not told anything about the products being present, so we can assume that we have none of those to begin with. Since we have no product present in our system initially, we're going to need to create some in order to get to equilibrium. So those product concentrations are going to increase as our reaction approaches equilibrium. And our reactant concentrations are going to decrease as we approach equilibrium. We need to consume reactant in order to produce product. So then we need to think about our coefficients. We have some invisible ones here and a few other things. So for every 1 mole of N2 that is consumed, 4 moles of H2 are consumed along with 1 mole of O2. So if X moles of N2 are consumed, 4X hydrogen and X oxygen will be consumed. And then for every 1 N2 that is consumed, 1 N2H4 is produced. So this will be plus X. And then we get twice as many water molecules formed as N2H4. So visible ones all around. At equilibrium, if we started with 0.1 molar nitrogen and we consumed X, we will have 0.1 minus X molar remaining. For hydrogen, we started with 0.1 and we consumed 4X, so we will have 0.1 minus 4X remaining. For oxygen, we started with 0.05 and we used up X, so we'll have 0.5 minus X. On the product side, we started with 0 N2H4 and produced X, so at equilibrium we'll have X. Water, we started with 0, produced 2X, so we will have 2X molar at equilibrium. Do make sure to notice that this water is a gas, so it is going to be included in this. Don't just assume that water is always a liquid. This one is water vapor, so we do need to include it in our table, and it would be included in our equilibrium expression as well. So in the next 2 videos, we'll be looking at different ways that we can actually solve ICE tables to either calculate the equilibrium constant or calculate the equilibrium concentrations of our reactants and products.